Hi everyone, and welcome to Asteria Aerospace's first ever Data Deep Dive. This is the Data Deep Dive for our most recent flight, Lyrid Flight 3. This was also our first flight ever with a payload on board, and the amount of data we received is very satisfying. We received exactly 9,389 lines of data, over 35 different channels of data, and 250 of those, or about 250, are actual flight data. Before we begin, I will stop for a moment to explain what our units are and how much sampling we get per second. We get 50 lines of data per second written to the SD card on the payload vehicle every 10 seconds. The acceleration is in meters per second squared. Angular velocity, or gyro, is in radians per second. Magnetic field strength is in microteslas. Linear acceleration is in meters per second squared. Gravity vector is meters per second squared. And our data collection devices are a BMP 390 barometer, a BNO 08 9 degree of freedom IMU, and a Adafruit M0 motherboard, along with a 350 milliamp hour battery, and all of these combined form our central computing core. I'll start by saying that down here we have our minimum and maximum values throughout the flight. We also have the delta, or the change, between those values, and at the bottom you can see all of the different types of data we're receiving. Specifically, I'll draw your attention to altitude in feet. You can see here that it says 183.39 feet change in altitude. You'll see in a little bit why that isn't exactly right, and why we put that in the video without realizing why that wasn't right. Now, continuing on, we'll move on to acceleration to start. This is acceleration over all 9,000 lines of data. You can see around here at 8,038, line 8,038, you can see the initial flight. You can see that it lands around 8,209, and then sits there up until just before line 9,000 when we pick it up and start to turn it off. A couple of interesting things jump out from this. First of all, you can see small oscillations right near the beginning where we were inserting the battery, micro USB, and turning on the whole vehicle. Next up, you can see out here at around line 3,300 where we put the vehicle onto the stand, and then you can see the good amount of time before the launch itself. Another interesting thing is that you can see this gray line, which is acceleration of z, is steady at about just below 10 meters per second of force on it. The z is the length of the rocket from nose to tail. Therefore, that is the force being pushed down on it by the Earth's gravity, which is around 9.8 meters per second. The fact that we can see the force of gravity on our sensors in this situation is incredibly interesting. We'll now move on to flight acceleration, which is just the acceleration from the previous graph, but cut down to the 200 or so lines of actual flight data that we got. You can see just before the flight starts, the vehicle is sitting on the pad normally. Then the flight begins and it gets stuck by the igniter still holding on and not igniting the second engine yet. You can see this by the dip in z acceleration here. What that is Newton's third law in action. You can see that the momentum is continued and the pod goes into a momentary weightless state. Then it accelerates up off the rail up to about 30 meters per second, which is a bit over 3 Gs of acceleration. You can see it coast at this for a while as it's burning the engine before it finally cuts out around line 100. You can see this now then drops all of the lines of acceleration down to about 0 meters per second. This is fascinating because it indicates we have a moment of weightlessness, lasting for a bit over a second here. After this, you can see that the nose cone detaches and the vehicle tumbles for just a moment, with the nose cone being disconnected from the vehicle and free before both of them hit the ground together. Additionally, you can see that after they hit the ground, X and Y, which are the sides of the rocket, are now experiencing the force of gravity, not in the full force that Z was experiencing it when it was the only thing experiencing it, but slightly divided so that both are getting a smaller amount of that force pushing down on them. Continuing on from flight acceleration, we move to flight altitude in meters. This is total cumulative meters rather than meters relative to the flight. We'll get to that in a few minutes. Here you can see that we start at around 1,845 meters above sea level. Then you can see it goes up for a moment, then continues up before coming down again. We'll now move to feet, where you can see that we start at about 6,040 feet before going all the way up to about 6,230 feet. Relative feet. This is where it gets really interesting. You can see our flight starts at 0 feet. Then it goes up for just a moment before stalling. This is seen in the video when we got stuck on the launch rail. After a moment, it frees itself again and continues up to apogee at around 174 feet. Then it continues down and lands a bit below 0 feet. This is where the inaccuracy within our launch takes place. To explain this accurately, I have to explain that our altimeter is not GPS based. It's based off of a combination of barometric pressure and temperature, which combine to form the altitude that it outputs. What's important to note about this is that rockets create quite a pressure change throughout their flight. Not just because their altitude changes, but also because the engines produce high pressure and high temperature gases out of them. You can see for a moment here we go up before getting stuck, but then for just another moment it drops for just a second. This is interesting because you can see that as we get stuck, it's likely that the rocket was enveloped in some gases from its own exhaust, which were higher pressure, and so it dropped its relative altitude guess for that. It then goes up, reaches apogee, and then possibly continues a little bit, but you can't see that because at this point the first ejection charge fires, bringing the relative guess of an altitude down a bit because the nose cone is now enveloped in high pressure gases from the ejection charge. You can see it start to rise again and then fall again a second time when the second charge fires. Then it tumbles to the ground and lands a bit below the launch site. This is what we didn't account for, is that the landing site of it was about 10 feet lower than the launch site. So we said 183 feet was our maximum altitude. In fact, it was actually only 170 or so, but since we calculated the change in delta, or the change delta from the highest point at 174 to the lowest point at about -9, you got 183 as a result of that. Next we'll move on to flight magnetic field sensing. There isn't a ton to see here, nothing groundbreaking for the flight itself. However, you can see a bit of oscillation near the start of the launch, and then you can see that the moment the vehicle, the nose cone, ejects from the main rocket body, the whole thing goes crazy, and you get a bunch of somewhat junk values because they're all reading different things. Lastly, we'll move on to flight gyro. This one is one of the most fascinating to me. Again, you can see it about 93 lines into the data. The nose cone separates and it all gets a bit jumbled. However, before then, you can see that about line 21, when we leave the pad, which is supported by the video, you can see that we instantly incur a bit of roll around the z-axis. Again, that's from the nose to the tail. Roll around the z-axis means that the rocket is rolling rather than actuating, rather than pitching or yawing. The interesting thing about this roll that we get is that this is in radians. Therefore, we can take the average of the approximate average of all the values we get here and see that for about 1.4 seconds, shown by the fact that we got about 75 lines of data, the average is about 6 radians per second. Therefore, being that there are 6.2 radians in 360 degrees, we can calculate that we turned about 180 degrees plus 360 degrees, so a rotation and a half. But that comes out to a cumulative of about 180 degrees turned over that entire amount. In total, it only turned about 180 degrees, even though it turned much further than that. So, with all this being the case, why did the vehicle pitch over at launch? This is because of an event called weathercocking. What weathercocking is when wind hits the vehicle as it's going up, and since it has fins on the bottom portion of the vehicle, but no aerodynamic surfaces that incur drag up at the top of the vehicle, the wind will hit the fins and rotate the vehicle into the direction of the wind. Since the wind was coming from the west on launch day, and we turned to the west, we are led to believe that this was part of why this happened. We also had asymmetric thrust, but we think that since we rotated so much during the initial thrust segment, that wasn't the reason why we pitched over. Especially since the total thrust duration of the motors is 160 seconds, and the amount of time that we captured of rotation is about 1.5 seconds, sorry. And the thrust duration is 1.6 seconds, we got 1.5 seconds, not 100 seconds or nothing like that. So, we believe that weathercocking is part of the reason why we pitched over, because the wind was coming from the direction that we turned, and therefore, because the fins got hit and incurred drag, the nose would pitch in the direction of the wind. We will be making this whole data sheet open source. We want people to be able to look through it and see what they can see. I would love to see if somebody finds something interesting new that we didn't notice. There's tons of lines that we just really haven't looked into because we don't have the time or knowledge to really understand and comprehend what they're all exactly saying. So I'm going to be making this open source. We'll also be soon making lots of the parts of our rockets open source so that people can build them as well. We'll probably make sure to put in some notes about what did and didn't work so that you can account for that in your own designs of the rockets. Also, next up, we've got some really exciting things going. We've got another rocket partially being built. It's in the process of being built. It's going to be using the same nose cone, and it will take off with a tube twice as long and on more powerful motors. I don't exactly want to say what those motors are going to be yet because I want to leave that to be a bit of a surprise, but it's going to be really big and really cool, and we're going to get so much more data from it. Additionally, hopefully we will get a parachute deploy from it, which we think the reason we didn't for that, since the parachute ejected, we just don't think it had the time before it hit the ground to deploy. So we're hoping for that on the next launch. Thank you very much for watching, and we will see you soon. Please make sure to like and subscribe. We're shockingly close to 1,000 subscribers, even though it may not seem like it, so please share it with people who you think would enjoy this stuff, and when we get to 1,000 subscribers, we're going to be live streaming these launches, so really excited for that. Thanks, everyone. Bye.